Okay, so welcome back. Let's begin with the second session of my survey talk. As I promised yesterday, today I'm going to talk about another property of Hitchin representations. So I think it's fair to begin with a very classical notion of another flow. So very generally, let's say M to be a compact manifold. And it's equipped with some C1 flow. And we say that this flow is another if let's say this is a smooth compact manifold, so that we can talk about this tangent bundle. So this flow is another flow if this tangent bundle admits a B T variant splitting to the three kind of component. This U, and this is the flow direction, where this is the kind of stable bundle, this is unstable bundle, this is the flow direction. This is a invariant splitting, such that this splitting satisfies the following condition. So in this direction, we have a contraction property. That means if we apply the tangential map and measure its distance, its norm, it decreases as we flow forward. So it means, on the other hand, on the unstable direction, we also have a contraction property, but we have to flow backward. For some non-zero constant, positive constant A and B, and for some choice of metric, and because our manifold is compact, this choice of metric is irrelevant. Any two metrics are by Lipschitz on a compact manifold, so it doesn't affect your definition. So this is a very classical notion of another flow. And what are examples? I think there are plenty of examples, I think, but the most relevant example for us is let's put it in the following form. So the geodesic flow on the unit tangent bundle. Let's say, let's use this notation. Bundle of hyperbolic surface S. This is another flow. So I'm not going to prove this, but I can describe it in a pictorial manner. So let's draw, because this is a hyperbolic surface, if you take a universal cover, it'll be a disk, let's say Poincare disk. And let's say, let's consider this unit tangent bundle over the Poincare disk. That's nothing but a disk, and pick a point and draw a unit length vector. That's the unit tangent bundle. And the flow, geodesic flow line through this point is nothing but the geodesic line that is tangent to this vector. So if we draw carefully, there will be something like this. And we have a point here. And let's collect all the geodesic line that are asymptotic to this particular point. That should be something like this. I'm quite poor at drawing. So imagine this. They're supposed to be perpendicular. So this is the kind of flow line, geodesic flow line on a unit tangent bundle of H2. And let's see let's draw some like cycle at this point, and we see the perpendicular vectors there. And when you flow in this direction, I mean forward direction, this relative distance between two vectors just decreases as you flow in this direction. So this is how we get the stable. This describes the stable direction of your Anosov flow. On the other hand, if we pick this point, we draw the geodesics cycle here, and we consider this direction. And when you flow backward, their relative distance decreases as you flow backward. So this is precisely describes the unstable direction. Let's say better to use this notation. So-called weakly unstable manifold. This is weakly stable manifold. So this is not a proof, but you can see what's going on behind this theorem. The Anosov representation is basically a representation that preserves this kind of contraction and dilation property. So let me give you a kind of precise definition for it. So this is definition. I take it from the Laboris original paper. So very kind of, before we give a definition, let me give you some setting. So let's say V is a gain compact smooth manifold with an Anosov flow. Let's take say M to be another manifold, smooth manifold. And let's say a Lie group Gx on M. And this M admits a pair of transverse foliation such that G invariant transverse foliation, let's say, minus, they are integrable G invariant splitting. And we say, sorry, I need to take we have Anosov flow, and we should have a discrete group that comes from taking the normal covering. Any normal covering is not necessarily a universal cover. And there's the depth transformation group gamma here. So in this setting, a representation rho from gamma to G is Anosov if there exists low equivariant and flow invariant map F from the normal covering to M, and there exists a continuous family of norms fiddle on the pullback bundle of Tn, such that, as I mentioned, this representation is supposed to preserve this contraction and dilating property. So that's what I'm going to write here, such that V, if you measure, is known at this point, supposed to be contract as we flow forward, or V comes from fallback of E plus comes from here, and we have a dilating property. If we choose a vector from the E minus part, or some, of course, positive constant ENP. So if we have those map and family of norms that satisfy this condition, we call it this representation an Anasov representation. Its definition is kind of very complicated, but I will give you a better definition at the end of this talk. So when we define some class of representation, we usually expect that the set of this class of representation form an open set in the character variety. So that's the case for the Anasov representation. So the first theorem is that set of all Anasov representations is open in the space of representations. So it's pretty technical, but so I just give you the most important idea behind this proof. So when you remember how we proved this Erasmus-Thurston principle, when you have a geometric structure, we make some kind of fiber bundle out of it, and we use some openness of transversality to prove that this Erasmus-Thurston principle. So we will do the same game here. So we have to translate all this definition in terms of fiber bundle picture. So let's say we are given a representation that we can associate a fiber bundle, say E of rho. How do we make it? Where we take the Hessian product between the normal covering and our target manifold and take the quotient. And this will be a fiber bundle. In this setting, this is not a, yes, this is fiber bundle, but we have an extra structure that comes from this Anasov flow on a manifold V. So we have the flow, say the flow, it's given by the following. We just flow on the V part only. And this flow just descends to this quotient manifold, give you some sort of flow. And in this setting, we say that rho is Anasov if and only if there exists a section sigma from the base to the total space such that the image of this section is actually phi T invariant set and it's hyperbolic set with respect to the flow given here. So this is if and only if condition. And that's the translation of our definition of Anasov flow in terms of fiber bundle picture. And once you have this, you remember how we proved the Erasmus-Thurston principle? And there we use the openness of transversality. We need we show that, I mean, kind of this holonomy. Our representation comes from holonomy if and only if there exists a transverse section. And the being transverse is Yes, V tilde is a universal, not universal cover. It's just fundamental, I mean, deck transformation. GX on M. And the transversality is an open condition. That's the crucial part for the proof of the Ehrman-Thurston principle. And here, we don't have a transversality, but we do have a hyperbolicity. And the hyperbolic, Anosov flow is also structurally stable, meaning that if you perturb a flow a little bit, it still gives you an Anosov flow. So basically, we have the same situation. You just replace the transversality with the hyperbolicity. So I think, and then we do the same proof as we did for Ehrman-Thurston principle. So I think there are some technicality, but this is the kind of main idea. And this is a very general picture, and we are particularly interested in the following situation. So our case, V will be the unit tangent bundle of our hyperbolic surface, of course, with the geodesh flow. Okay. And V Twitter, this is the normal covering, and in our case, there will be the unit tangent bundle over the Poincare disk. And then, of course, deck transformation group, over V will be just a fundamental group of S, and all denoted by gamma. And our G, Lie group G, will be either PSLNR or SLNR, but I prefer SLNR here. And our manifold M will be the G mod A. I'll describe it what they are. And they are sitting inside the following product manifold, plus times P minus, where P plus is the set of all upper triangular matrices. And P minus, you can expect, is the lower triangular matrices. And A, so-called the Cartan subgroup. This is the intersection of P plus and P minus. There'll be just diagonal matrices. That's our setting. And in this setting, I believe I can erase this. Very, very hard to erase. So let's say remark. They are kind of complicated quotient manifolds, but we have a concrete description in terms of homogeneous space. G mod P plus, this will be called the Flagon manifold. And this is nothing but a set of all ascending chains of subspaces that up to n, where each of VI's are subspace of Rn. In this dimension is precisely and we collect all of these ascending chains and give some appropriate topology. Whereas G mod P minus is also morally the same as this Flagon manifold, but it's kind of opposite in the sense that we now have a descending chain condition, not descending chains of subspaces. So when you have this, and this is the largest, this Rn is the whole Rn space. There's the one dimensional lower than this. beta and 1 here. And the dimension of k would be n minus k plus 1. And of course, m, this is just a set of frames. But in terms of flags, I can write it in this way. So flag Rn times flag opposite Rn. And they satisfy some transversality condition. This is direct sum. So say if you pick this space and pick this space, they form a direct sum, giving you the whole space Rn. So if you pick this and this, they also give you a direct sum, this whole space Rn. Okay. So kind of any questions so far? And then I'll give you a very trivial kind of example, but I think this example describes, it's complicated enough to give you more sense about this definition, what's going on behind the definition. This case, or let's say SLNR, SL2R. So kind of obvious example. And gamma will be, of course, pi1 of S sitting inside our G as a co-compact lattice. And then our F, this map F here, is the, of course, from here. But I don't know whether you know this, but the unit tangent bundle of H2 can be naturally identified with the PSL2R group itself. So we just use this identification, and G mod A will be just a projection map. In this setting, I want to show that this representation is actually an Anasov representation. So to do this, I need to give you a kind of continuous family of norms in the pullback bundle. So let's say pullback of the tangent bundle of this space at the identity. I can write it as follow. This kind of matrices, direct sum with a lower triangular matrices with zero diagonal. Then let's generate P plus and P minus. So this particular tangent space at this single point can be written in this form. And we, with the norm, say 0, 0, xy, and just give the standard Euclidean norm. Then you give left invariant norm, just like translate all these pictures to everywhere by the left multiplication. And then this becomes automatically low equivariant know. Right. And now we want to compare, and then I have to mention this, like in this setting, geodash flow can be written as a right multiplication by the diagonal matrix. Say geodash flow passing through G is either you can, this is a member of group element as well as a member of unit tangent bundle. Nonetheless, this will be just G times e to the t minus t 0, 0. That's the geodash flow. And then let's compute very obviously T of E. And because I gave the left G invariant norm, this will be this E, just translate it by this vector. And then that's minus T, 3, 0, 0 at E. And then this is nothing but so we have a contraction property along P plus direction. And we do the same computation, then it will tell you that along this P minus direction, we have a dilating property. So this is a Hausdorff representation. And then it looks kind of simple example, but the same principle applies to the Hitchin component, namely let's say, remember we defined the canonical irreducible representation. This guy. And then this Fuchsian representation. This is also an Hausdorff representation. We just do the same game with like bigger triangular matrices and bigger diagonal matrices. And you do the same computation basically. I tell you that we have the same contraction property. And now let's discuss the Riemann map. I think that's the most important feature of Hausdorff representation. So before we go to the next section, if you have any question, please feel free to ask me. So let me begin with a small definition curve C from S1, this one-dimensional circle. The flag manifold Rn is called two convex if for all k 1 to n minus 1, the following sum is direct, giving you the total space Rn for any two distinct points in S1. That's the definition of two convex curve. Pictorially, let's say something like this. This is good. This is two convex because let's say pick a point here. There will be a say so I, and we have a 2 here, And this line, and if you pick another point, say here, and this line spans R3, right? If you do the same thing everywhere, let's say C and any point here, so they also span R3 as a direct sum. So if this happens, we call it, two convex curve, but it's not. Oh my. Bad example looks like something like this. If you pick, say, here, and say this is 2x here, and you pick this point, say P1 of y, and then this line and this point doesn't span the whole space Rn. So because we have such a bad point, this curve is not two convex curve. So the theorem that I want to mention is that if you have a Nosov representation, then you can always find a equivariant two convex curve into the flag manifold. So the theorem 생각보다 굉장히. So let's say this is a Nosov representation, but this is true only for the surface group case. Then there exists no equivariant two convex curve from the Gromov boundary, your surface. That would be topologically S1, but the target manifold is of course flag manifold. Let me give you proof. How do you make this limit curve? By the way, this curve will be called the limit map or a Nosov map. Yes, either like limit map or Nosov map. So because our representation is a Nosov, we have a map from the normal covering to the product of flag manifolds. And the unit tangent bundle of Poincare disk actually can be written as follow: S1 times S1 minus, say, big diagonal. That means YZ, let's say, X1, X2, X3, Xi, Xj, or distinct. No, I have to remove this part or some I and j. And how do we identify this? Well, as I told you, unit tangent bundle is nothing but a point and a vector here in the Poincare disk. And then, if we are given this configuration, we can draw a geodesic that's tangent to this point. And we have two endpoints here, say x and y. This specifies a single geodesic, but we need to specify this point. To do this, we draw a perpendicular line, another geodesic here, and this will give you a z, another point here. And we assume that this is kind of cyclically ordered. And this way, we can identify a single element here with the triple of S1 points, and the diagonal being removed. Okay, this is the identification, and you can see that the geodesic flow is nothing but to move this G point, the middle point, somewhere here or somewhere here. F. And because, remember the definition of Anosov representation, this F is actually a flow invariant map. So even though we have a map from this space into this space, it factors through S1 times S1 minus diagonal. So let's say this is F tilde. We just ignore the flow part, say middle part. This is kind of flow direction. And then, because we have a product space, we can of course project down to each component. And then let's say just define show plus or minus to be plus minus composed with F Twitter. Good. And we claim that this plus, we have a two argument, you see. We have a two arguments, X and Y. But this is the same as, it's independent of the second argument. That's basically the claim. And if you look at the minus part, we have it doesn't change when you varies the first argument. So how do we prove this? Well, do I have enough time? Yes, I think so. So let me draw something. So the picture is this. We have a Poincare disk, and you have X here, and say we have Y here, and W here. And let me draw a reference holocycle. And this gives you some parameterization in this curve, parallel curves. And then, so reference holocycle. Yes, such that, let's say this is V, 0, V1, that H of 0 is V0, and H of 1 is V1. Then we define HT of S to be the flow by the geodesic flow. Basically, you just say something like this. This is HT of S. Very bad drawing. And then we define the following map. T, the pi plus minus composed with FTS. Okay. I put T here, but because it's F map, F is kind of is flow invariant. This is actually independent of T. So I can just write in this way for T. And you can observe that gamma of 0 is nothing but the gamma plus of x, y, and gamma 1 is just h plus x and w. Then we compute the following quantity. U of t, this is the length between these 2 points. If they are not equal, this quantity will be positive, definitely positive quantity. Yes. So basically, we measure this length with respect to the metric. And because if you assume that if push x, y is not the same as x and w, then dt is always positive for all t. But because our manifold is compact, by compactness argument, this quantity must be bounded from below by some positive number for all t. However, by the Anosov property, this metric, this norm, decreases as time goes forward. This is decreases. Therefore, this quantity must goes to 0 as t goes to infinity. That's the contradiction. So we must have the same value regardless is the second argument. And the second part is just the same. And now we can define this limit map. So the limit map rho will be the x times y, whatever y. Because this is independent of y, we just put any y here. But we have the similar property here. So why don't we have this limit map? Y, x not equal to y. So basically we seems to have two different limit maps, but actually they are very closely related. The following sense. The claim, second claim. This is nothing but I wrote hat here. X opposite. I think I can't prove this in time, so I just skip this proof. But once you have this, we have the following x. We don't know yet whether this is direct or not, but we will see this, why this is direct sum. This is equal to this, and we assume this, that we have switch opposite, but the opposite is nothing but replacing this. And this is by definition a of x, y. This is k, y minus, and yes, that's Rn direct sum. Because it has an image in M. This is a member of M, and I erase it, but this M is characterized by transverse flags, and that's why we have a direct sum here. So we know that the limit map is actually two convex curve. This is a definition of two convexity. So that's the proof. And I have to mention that this limit map is unique without proof. And let's see some kind of obvious example. Any questions so far? Yeah. F tilde. This map is previous. I mean, in the beginning we have this map, but because of we can identify this with triple product minus some diagonal, and because this map was flow invariant, we can ignore the flow direction, and this is I can say this is a flow part. So we just factor through S1 cross S1 minus diagonal, and this F2 here is the induced map. So for example, if we have a Hitchin component, I mean, PFL3 are Hitchin representation, and this associates, and rho is a holonomy of convex projective geometry on S. That's nothing but can write it as a quotient of some convex domain by this. And in this case, our limit map is nothing but, I mean, more precisely, the image of limit map. This is nothing but the boundary of closure of our domain of discontinuity. This is kind of example. 네. And then I have to prove some theorem, but let me skip the proof, but I just stated. If you have a Nusselt representation, and if you have a non-trivial element from your group, then when you evaluate it at your Nusselt representation, then this is diagonalizable. So, I mean, let's say this way, conjugate to the following matrix, where lambda 1 is largest. This property holds for arbitrarily Nusselt representation, not just for Hitchin representations. Then, now we can characterize Hitchin component in terms of Nusselt representation. So that's to do this, I need some more definitions. So one to objective for n is Frenet, I mean, not Frenet, hyperconvex. For all, if say, it's one dot C of x2, C of x n is the direct sum, giving you the whole space Rn for all distinct xi's. that's the Frenet curve. I mean, hyperconvex curve. In the theorem by Bouchard and Laborie, remember, if you have a Nusselt representation, we have a two convex curve. And that's too much, just actually very too big for a representation being Hitchin. So we just say that, can say that the rho is a Nusselt. And this is, and then rho is Hitchin. If it admits a very special limit map, namely this associated limit map is hyperconvex. If and only if. So if you have a map, the limit map is hyperconvex. If you know that this is a Nusselt and its limit map is hyperconvex, then it must be Hitchin. So that's another characterization. Let me, sorry, I'm running out of time. But, let me give you as I promised, the most simplest definition for the Nusselt representation. That's the modern definition. Definition by Portree and Sambarino. Saying that always a Nusselt if K and Nusselt, if there exists a constant A and B such that the kth eigenvalue over K plus 1 eigenvalue is bounded from below by constant times exponential times B times the word length of your group element. So if this were my largest singular value of. So this is the simplest definition for representation being a K and Nusselt. And if it is like a Nusselt for all K from 1 to N, then that would be called the Borel Nusselt or just a Nusselt. Just a Nusselt. In the sense of Laborie. Yes, I think I run out of time, so I have to stop here. And after a 10 minutes break, I'll give you, I'll present some recent work with Seong Choi about the volumes of Hitchin moduli space.